45 minutes later. And going to end, like he's like doing the entire thing where it's like,
Okay. Ready. All right. As you can see, we're starting out with a little bit of practice understanding our pressures related to ventilation. Pulmonary ventilation being the process of breathing in and breathing out. So our inspiration and our expiration, which is what we're going to be continuing with today. Okay, so we got a couple little math problems, sort of, in here. All right. So what we want to remember from last time first is what these forces mean. That's why I got a little picture for us on the side. So before we get into any of the actual scenarios, let's make sure we know what we're talking about. Okay, so when we are looking at these pressures, we're thinking about three of them: the pressure of the atmosphere, the pressure of the alveoli, and the pressure of our intrapleural space. All right, so outside, we're going to have our pressure of the atmosphere. So this is just the pressure of the air you breathe outside in the world. That's PATM. Our pressure inside the alveoli, we'd find in here, those little yellow grape things are our alveoli. So this is essentially our pressure inside the lung. And on the zoomed in picture, we might draw it here. And our third pressure that we're paying attention to is our pressure in the intrapleural space. So the intrapleural space is the fact that our lungs are inside a sac that has like two walls so they can slide against each other. So when we take this cut and zoom in, this blue part is that space. So this is where we're going to find our intrapleural pressure. Okay. So these are the three things we're looking at in this table. And we might note immediately after we look at our numbers that what we see are relative pressures. So we've set the pressure of the atmosphere to 0 in all of these cases so that we have easier numbers to work with, essentially. Okay. So as we're moving through each scenario, we want to first figure out whether air is moving in or out of the lung. And then we're going to add on this concept of transpulmonary pressure so that we pay attention to all of these numbers. Okay. And I say so that we pay attention to all of these numbers because all we have to do to figure out the air movement is compare two of these pressures. Which two would those be? Anybody want to volunteer? So we're going to be comparing the pressure in the atmosphere to the pressure where? Yeah, the alveolar pressure. Okay, so we're comparing our pressure in the atmosphere to our pressure in the alveoli, which is just the pressure inside our lung itself. And using just those two numbers, we can figure out whether air is moving in or out of the lung. We're going to proceed forward. So everything's a little shifted. I guess I will clear those annotations. Okay. So as we compare for our first scenario, the pressure in the atmosphere to the pressure in the alveoli, we can note that our pressure in the alveolus here is less than the pressure in the atmosphere. So we have a negative pressure in the alveoli and negative pressure in the lung. Okay, so our pressure gradients work the same as all the other gradients that we've seen in this class. So we have movement from high to low. So in this case, 0 is our high number. And we're moving towards those alveoli because we have that negative number, that lower number. Okay, so this is how we figure out that this is inspiration, inhalation, air is moving into the lung. Okay. Now the second part is where we think about our intrapleural pressure. So as we start to think about how we created this negative pressure inside the alveoli, we might pay attention to what's going on across the wall of that lung. So we mentioned this idea of having like a distending pressure, so a pressure that causes the lungs to change their size. So this is our transpulmonary pressure, which is just going to be our pressure in the alveoli minus that intrapleural pressure. So we take our -1, subtract out -5, so we're adding 5. So we'd get a pressure of 4 here across the wall of the lung, or transpulmonary pressure. Okay. So we can do that with each of these examples. Okay. So in scenario 2, we've changed our numbers. So we still have an atmospheric pressure of 0, but now we have a positive alveolar pressure of 1, which means that we are going to be pushing air out. Okay. So we're pushing air out because we have this higher pressure now in the lung compared to that lower pressure in the environment. Okay. So we could then calculate our transpulmonary pressure with these other numbers. So 1 minus 4 in this case would be a -3 here. Finally, we do see some situations where we have reached equilibrium between the atmosphere and the alveoli. So when they're at the same pressure, we are not going to see movement of air at that particular point because we don't have a pressure difference there. Okay, so we don't have a pressure difference, but in this example with these numbers, we do still have a transpulmonary pressure. Okay, so we still have a transpulmonary pressure here, so we might expect something to change about this soon. So that's where we left off. Oops, sorry. Copied something too many times. Okay, so this would be air in, and that was our -1 plus 5, so that was the 4. Okay, so this is that whole table out, right? So we can calculate pressures in this way. The most important thing we want to notice is that we're just comparing that alveolar pressure to the atmospheric pressure in order to figure out how air is moving. So we're now going to think a little more deeply about the alveoli, their pressures and their volumes, and like why we might have a higher or a lower pressure in an alveolus. Okay. So to understand that, think back to chemistry and think about the ideal gas law. The equation for that is PV equals nRT. What we want to take away from it for our understanding of physiology is really just this relationship between pressure and volume. Okay, so we're looking for this relationship between pressure and volume. We're going to consider our N and our T constant and R is constant as well. Okay, so what we're taking away from this is that we're essentially going to have a trade-off between our pressure and our volume, right? So because we're keeping these factors constant, they're saying the same number. This means that if one of these goes up, the other is going to go down, essentially, right? If we want to keep that constant number. Okay, so I've said this to you a couple times without showing you math, without showing you gas laws, right? But all we're trying to say here is that as we have the size of a space, this volume of our container changing, that changes the pressure of the stuff inside it. So we can see that drawn out in these diagrams. So we have the same number of little gas molecules here in this larger container. So it has a volume here, in this case, a volume of 2. All right. If we shrink that container, but don't move any of those molecules, they're now packed way tighter, right? So we've decreased the volume, but because we didn't change anything else about this, right? We kept that same number of molecules here, didn't change the temperature, didn't change anything else. Our pressure has now gone up because they're packed in tighter, okay? So we want to be thinking about this conceptually as we think about the alveoli and the thoracic cavity as a whole, because we're going to see that your chest, your thoracic cavity is going to be changing its size, changing its volume. Okay. So that's going to affect the pressures inside your thoracic cavity. Okay. And we're also going to see that following along at our little zoomed in level. So those alveoli are also going to be experiencing changes in pressure and volume. Okay. So all it is when we change the volume of the container, we also change the pressure in the opposite direction. All right. So our determinants of that intraalveolar pressure, which is our pressure in the lung, so our PALV is how we note it down, okay, is going to be dependent upon how much air is in the alveolus. So that's those little gas molecules from the previous image, right? And the volume of the alveolus, by which we really mean its size, essentially, right? So how big, how small it is. That's our measure of the size of the alveolus, which is our container for the air, okay? So as our lungs expand, as our lungs get bigger, they contain the alveoli within them, right? So they contain the alveoli within them. So lung gets bigger, alveoli get bigger, okay? They just go along with each other. So if we're picturing, and I think this picture is on future slides, if we're picturing a little alveolus, right, start out small, we're going to make it get bigger, right? So what we're saying here is our volume went up, okay? We have a trade-off between the pressure and the volume, right? So our pressure, comparatively, is going to go down, okay? So as the alveoli expand, as they get bigger because the lung is expanding, this drops the pressure in the alveoli, okay? This is what can create that negative alveolar pressure. Right, so let's make it, I don't know, -4, right? Okay, that's what can create a negative pressure relative to our pressure of the atmosphere, which we always set equal to 0, okay? So what we're saying is that by expanding the alveolus, making it larger, we create a drop in pressure, which is how we can create a negative pressure overall. Compared to our atmospheric pressure of 0, this is going to create a pressure gradient, right? So we got higher over here. We have lower over here. Our air just follows that gradient. So it moves from the atmosphere into the alveolus. So that's what we mean when we say that we have a pressure gradient driving air into the lungs, is just that when we compare those two numbers, we have a difference in pressure. Air is going to move towards wherever there is lower pressure. So by expanding the lungs, expanding the alveoli, changing their pressure, dropping it down, we are able to move air into the lung. So that's how we're going to start out when we breathe in. Okay. So when we then breathe out, we're going to have the opposite thing happen. Undo back to our first two alveoli that are different in size. Right, so now we're just going to step the opposite direction. Okay, so we're going to say that we're starting out with that large alveolus. Right, so this is now going to be 10.1 on the right here. Okay, so as our lungs recoil, bounce back, right, we're then going to see a change in the pressure and the volume again. Okay. So they had their separate volumes. We're now starting on the right. So we're thinking about moving towards that smaller, okay, that smaller one. Okay. So as we're decreasing the volume, this means that the pressure does the opposite thing and it increases. Okay. So we would now start to have some type of positive pressure. Okay. Whatever, just going to pick a random positive number. Right, so we could compare that to our pressure in the atmosphere. Okay, All right. So compare that in the atmosphere. This is now our higher number. So we now have a higher number inside the lung compared to outside your body. Okay. Which means we're now going to have movement out. Okay. So for like associating this with your body, let's sort of think about this and take like a deep breath in and a deep breath out and put your hands like somewhere on your chest where you can feel it move in. So take a deep breath in and hold it for a second. So you should feel your chest wall moving out and let go. Okay. So that's what we're talking about. So maybe as we're talking through this lecture, feel free to breathe and try and compare to what we're doing. But you might have noticed, right, that all you had to do to release that air is you just kind of have to relax. If you breathe in and then just let go, the air goes out. And I'm telling you that because what's happening is your lungs are recoiling, right? So they're just kind of bouncing back, right? So you can just relax in order to get back to the smaller state. So when we see relaxed breathing out, we're really just going to see relaxation of everything. Whereas to expand the lungs, we're going to have to actively use our muscles. All right. So we'll look at a chart of inspiration, breathing in, and expiration, breathing out. Okay. So we see here a chart of our intraalveolar pressure, okay, which is also listed up at the top. So our PALV, okay, we remember our pressure of the atmosphere is always 0, right? Because we've set it equal to 0. It's really like 760 at sea level. Okay. Okay. We now see a cycle of breath. So breathing in, pause, breathe out. Okay. So at the bottom, we can also see the breath volume. So what this is showing you is like how much air is in the lung. Okay. So we can see that as you begin to breathe in, so we're going to start at 0. Let's do this. All right. So we're going to start at 0. So we're starting at equilibrium with the atmosphere. So we're starting at a pause. All right. So we're going to start to expand the alveoli in order to breathe in. So we're going to pull our lung out. We're going to make it bigger. We're going to make that space bigger, which makes each alveolus bigger. So we can see our change in size. Okay. So that change in size, first without a change in this number of molecules. So we had 2, 4, 6 here. We still have 2, 4, 6 in the second image. Right. So the first thing is we're dropping that pressure without moving air in for a second. Right. So we drop from 0, we expand the volume. So our volume of the alveolus went up, it got bigger, which means that our pressure has to go down. Okay, because we didn't move air yet, which is how we get here to our pressure of -1. Okay. What happens next is that we do actually change how much air is in our alveolus. Right, so we're changing the amount of air in the alveolus. Okay, so when we get to that -1, our air is moving in. Okay, so now we're going to have more molecules inside our lung. Okay, so they're now filling that space more densely. Okay, so their quantity is going up. So this is going to fill that space back up and bring us back to equilibrium. So that would be like changing the n in the previous equation. So that's how we get back to 0. Even though we have a large alveolus, we changed the amount of stuff within it. Okay, so we changed the amount of stuff here. And then we're going to relax our muscles and the tissue is going to bounce back. Okay, so that's the recoil part. But now we have more stuff than we did. Right, so we have more stuff, more air, more gas molecules inside that alveolus. And we are pushing in or recoiling the wall of the alveolus. Okay, which means essentially we are decreasing the volume of that container, okay? Which means we have an opposite change when we think about the pressure. So now our pressure goes up. Okay. So the pressure is now going up with these molecules here. That's how we get to this higher pressure. Okay. That's how we get to this higher pressure, which is then ultimately going to force air out because we have a high pressure inside versus a low pressure outside. As air actually physically moves out, even though we have this smaller alveolus, we eventually come back to equilibrium, back to zero. We've equalized the pressure in our lung to the pressure in the environment. Okay. So this is how a cycle of breathing works overall. So we picked out just a couple time points. So the extreme points, maximum and minimum of these pressures here. But this is a gradual change happening, right? So we are getting more and more and more negative, right? Then a bit more positive until we hit zero, more and more positive. So we are going to be breathing volume in progressively. Okay. So we can see that during inspiration, our breath volume is going till we hit equilibrium with that larger size of the alveolus. And at that point, we have more air in our lungs, right, than we did at the beginning. But that's okay because we have this larger alveolus, right? So we have two different conditions where our atmospheric pressure of zero is equal to an alveolar pressure of zero, but they don't necessarily indicate a specific amount of air in the lungs because they have to take into account how much gas is in what specific size of alveolus, okay? But then we push it out as we go back to our original size. So that's how this might look in graph form, okay? So I would recommend kind of working through this on your own as you're studying, explaining to yourself what's going on here at these different pressures with a cycle of breath. But these are just in total what is going to create our forces for inspiring and expiring, inhaling, exhaling. I don't know if it says preparing still. Okay, well, I hope that's okay. So when we're thinking about the mechanics, we're going to start thinking about like the mechanical forces. So we're really thinking like muscles that affect this change in size, affect this pull on the lung, and ultimately create this alveolar pressure. Okay. So we refer to muscles as inspiratory if they're helping you inspire, if they're helping you breathe in. Okay. We call them expiratory if they're helping you expire, exhale, breathe out, right? That's the X. So towards the external environment. Okay. So we know that to breathe in, right? To breathe in, we have to decrease the pressure of the thoracic cavity, right? So in order to inspire, what we're saying is we need our alveolar pressure to go down, okay? Which means because we have a trade-off with volume, we're going to need muscles that make that volume go up, okay? So that's what's happening with our inspiratory muscles versus expiration, right? We want our pressure in the alveoli, so our pressure in the lung, to go up, right? Because we're trying to force air out, which means we're getting our volume to decrease in order to create that change in pressure, okay? So this is why we can say that our inspiratory muscles are going to increase the volume of the thoracic cavity. So they're going to make your lung bigger, they're going to make your chest bigger. And our expiratory muscles are going to squeeze down, decrease the volume of the thoracic cavity, make that size smaller so that that pressure goes up. So we do have specific muscles that do this. The main muscle that we think about when we think about breathing is one of our inspiratory muscles. That's your diaphragm. So your diaphragm is located between your thorax and your abdomen. It's really the divider, right? So you're going to see it attaching down at the bottom of the ribs, right? And this is the one that I asked you to think about a little bit before, okay, because the diaphragm in its relaxed state, when we think about relaxed muscles, we want to think about longer, looser muscles. So it's relaxed. Diaphragm is just like long and curved up. It contracted, so like active. Contracted diaphragm. We're making those sarcomeres shorter, right? So it's going to be flat. Okay. Now our thorax is located above it, right? So it's like here, here, right? So you can see that as we contract, right? If we look at that area of the thorax in this relaxed state, we have some amount here. But as it flattens, as it contracts, your rib cage, where your shoulders are and so on, is kind of stuck in place. We're not changing the top part, we're just changing how far down it goes. So we can see that this is a bigger volume in that thorax with the diaphragm. Okay. So this is the main muscle that we use to breathe. And I say the main muscle because when the diaphragm relaxes, it goes back to this relaxed state. This creates a really big change, which creates expiration as well. So it's not listed under the expiratory muscles because we're only talking about what's happening when they're contracted, what's happening when they're active, right? But our breathing out, our exhaling, our expiration is largely going to have to do with relaxing these muscles, relaxing our inspiratory muscles. Okay. So this is our diaphragm. So when the diaphragm moves down, when the diaphragm is active, it makes our thoracic cavity bigger. Our external intercostals, so our outer layer of muscles that go between our ribs, also contract to increase the volume of the thoracic cavity. So that's what you feel when you put your hands on your chest and you breathe in, right? You can feel that your sternum is kind of coming up, your ribs are coming out to the side, increasing volume in both that anterior-posterior direction and that medial-lateral direction. Okay. So that's what they're doing. For our expiratory muscle, it is true that our internal intercostals and our abdominal muscles can decrease the volume of the thoracic cavity. The internal intercostals have an opposite fiber direction to the external intercostals, so they just do the opposite thing. Okay. The abdominal muscles basically make the space for your abdomen less, which is going to push all those organs back up into your thorax, which also has the effect of decreasing the thoracic cavity. My cough was actually perfect, so I want everybody to like take a big breath in and then like tense your abs. Right? You make that sound? Everybody do it. Come on. Right? Okay, so you can feel that, but that's forceful exhalation, right? You're not doing that every single time you take a breath. Okay. Usually when you're relaxing, you're just going to relax these inspiratory muscles. Right, so here we see pictures of where those muscles are, right? So our external intercostals between the ribs running with this fiber direction, just like kind of putting hands in the pocket, right? That's going to be our direction. Okay. Our diaphragm is this dividing point underneath. Okay. This is a picture of its relaxed state where it would flatten out in its contracted state. And then we can see deeper down, those internal intercostal muscles are going the opposite direction. So they do the opposite thing. Plus our abdominal muscles could force organs back up. So we could draw, this is a really bad stomach, but imagine it's a stomach, right? Tense your abs, it's going to like push it back up. Okay. Right. So that's how we're changing the volume of our thoracic cavity in order to change the pressure in the lung. So here we see a different sort of view of what's going on. So this, we've taken a cross section. So we've like cut through like that. And we're showing what's happening if you go through a rib and look kind of up or down. Okay. So because of those external intercostals, they are going to pull the ribs out to the sides and they're kind of going up and out. Okay. Sternum's doing the same thing. It's attached to the ribs versus the internal intercostals. And those internal ones do the opposite thing because they have an opposite fiber direction. So they're going to pull the ribs down and in. Okay. So we're expanding in multiple directions. Diaphragm, right, is expanding us up and down, really up and down, right? So in this direction, the superior inferior direction versus our external intercostals are moving us out side to side, as well as forward to back. So we're making our chest bigger in all the ways that we can. So we can think about this as a pathway as well. So breathing is controlled by centers in your brainstem. So what they're doing is when you want to breathe in, you got nerves that go to those inspiratory muscles. So your brain's sending a signal to your diaphragm and your external intercostals. That diaphragm flattens, pulling down, making that space in your chest taller, right? Making that thoracic cavity taller. Those external intercostals, as they contract, are pivoting your ribs up and out, okay? So we're expanding side to side and front to back, okay? This is making our thoracic cavity increase in volume, right? Increasing in volume, which means ultimately we're going to be dropping down our pressure, okay? Because this is a trade-off. We have some intermediate steps we might think about here. So if we're thinking about all the steps that would have to happen when we contract those muscles, what they're actually pulling on, right, are the bones. The bones are going to be attached to soft tissue. So like membranes and layers of stuff, right? Including our pleura. So that sac surrounding the lung, right? So we have parietal pleura lining the inside of our chest wall, okay? So as that parietal pleura is moving out, following along with the ribs and the muscles, this is also dropping the intrapleural pressure, right? So that's actually what happens first, drops the intrapleural pressure. Because our intrapleural pressure, okay, is our alveolar pressure minus our intrapleural pressure, that's our transpulmonary pressure. Okay, so as we drop this number down, we're subtracting a negative, which means our transpulmonary pressure, if you subtract a bigger negative number, it goes up, okay? So this is the force that ultimately causes those alveoli to expand because they have a pressure pulling on them, essentially. So as the alveoli expand, that's the volume we're ultimately caring about when we're looking for alveolar pressure. So our pressure drops down. Okay. So this is what creates our flow into the alveoli. So we know that flow is going to be our pressure gradient divided by resistance. So what we've done is we've just created a difference in the pressure between our atmosphere and our alveolus, right? So we now have a negative alveolar pressure. So it's pressure gradient. So we're going to have flow. It's going to flow in towards that lower pressure. So we could step that through in the form that your book likes. I'm going to see if there's a button I need to push to make that go away.